Okay, yeah, today's speaker is Torres Castillo from BilTop University, and he's going to tell us about partial group cohomology. So please,
Yes.
Victor, start.
Okay. Well, I'm happy to be here today in person. My first talk in person at BilTop. So, to talk about partial groups, I would like to give historical motivations, how they were originally defined. So, let's uh, let's start by giving some motivation. Okay. First of all, partial groups, pre-groups, localities are group-like structures, and we, well, everybody here know the notion of a group. Okay, to any group, we can associate a space called the classifying space of G. Okay, as this is a space, this fits into the field of topology. Well, from G, when we can induce the space Bg, the classifying space of G. The name is because of it classifies the principal G bundles. That's why the name. Okay, but we can recover G up to isomorphism from Bg, applying the fundamental group. Okay, so fundamental group pi 1. Well, a construction for the classifying space, we can use, for instance, the Miller construction. Well, now we can also study the group locally, P locally, by studying if it's a fusion system associated to a Silo piso group of G. Okay. Now in topology, we can also study P locally a space by P completing the space. Okay. We can P complete the space, and this construction isolates the P mod information of the space. Okay. Again, from the fusion system of G, we can induce a space that is equivalent to the P completion of Bg, but also from Bg P completed, we can recover up to isomorphism the fusion system of G. This is the Martino-Priedi conjecture, which was the hard. Okay. This direction was the Martino-Priedi conjecture. Okay, and this was a result by I guess Misling, Oliver, because this was conjectured by Martino-Priedi, but finally proved by Oliver. Okay. This is the P-local structure of G. And this is the P completion of the space. So this Ah, okay. This is the other way. Okay, okay. Sorry. Okay. Martino, Reedy, Oliver. Okay. Well, what is a fusion system? Yeah, a fusion system is a category in general over a P group S, a final P group S, is a category a final fusion system F with objects are the subgroups of S and morphisms satisfy this condition. Morphisms between P and Q are injective and they contain the conjugations induced by elements of S. Okay, well, this is well, homomorphisms such that phi is a conjugation for some element S in the group S. Okay, now there is a particularly well-behaved class of fusion systems that are called saturated fusion systems. So the saturation actions are a bit technical, so I won't give these actions, but they are of interest for homotopy theories because we can talk about the classifying space of a fusion system in this case. Well, example of fusion system, for instance, well, F is a fusion system of a group G over S, where S is a silo piso group of G. Okay, and F of PQ is the homomorphism from P to Q induced by well, conjugation by elements of G. This is the fusion system of G over S. We say that F is realizable if F is isomorphic to the fusion system of G over a silo piso group of G. Well, there is a notion of isomorphism between fusion systems. And when F is not realizable, we say that F is exotic. Is exotic. Okay, so we are interested in the exotic cases. For instance, these fusion systems are saturated. In saturation options are intended to imitate the CLO properties. So an example. By Solomon. There exists exotic function system F so Q. This is the notation over S, where S is the CLO 2 subgroup of this group, spinor 7Q. And Q is a power of a prime n, of a prime p. Okay. Well, this is an exotic fusion system, and Benson defined a space associated to this fusion system. The construction is a homotopy pullback, I guess. Just a moment. Okay.
To clarify the attribution, I think there was no concept of fusion system was not even defined when Solomon was doing his work. It was a part of an argument of his by contradiction, right?
By the time of Benson, do you mean?
Yeah, I mean when Solomon did his work, there was no, as far as I know.
I don't think there was. I thought it was proposed by the group.
Did Solomon phrase it in his terms?
Well, it calls it a forbidden system, but his axioms, I believe, were equivalent.
What? Now, let's talk about the classifying space of a saturated fusion system. Well, the Solomon fusion systems are saturated, okay, but it's not trivial to check if I remember well. Okay, so to this fusion system, Benson constructed a space, and he said, well, this could be considered the classifying space of the Solomon fusion system. So how was it constructed? Well, he used let me check. Okay. He used well, this is a two compact group. Like it's a homotopical generalization of a compact Lie group at the prime 2. in fact, there is only two. There is only one exotic two compact group. And this guy is the classifying space of this two compact group. Okay, so we have here the diagonal. Here we have the Adams operation in some sense. There is a notion of Adams operation. So we take the homotopy pullback and we obtain the classifying space of the Solomon fusion system. Well, actually, we defined this homotopy pullback as the classifying space of the Solomon fusion system. Well, oh, sorry. This is the, okay. Is the one component is the identity and the other component is the Adams operation. Okay, so it's nice to have a space associated to this fusion system. And later, Brotto, Levy, and Oliver started working on the theory of fusion system and then associate a space to these fusion systems. Well, when they are saturated, okay. In general, we have a functor from the centric orbit category is the name, if I remember well. Of the fusion system F to the homotopy category of the topological spaces. Okay. This sends an object, well, P is a subgroup of S, it's a centric subgroup of S, and this functor sends P to the classifying space of P, sorry, and sends the class of phi to the class of the map induced by phi. Okay. So we would like to take the homotopical limit of this functor, but this is defined to the homotopy category of the topological spaces. To speak of the homotopical limit of this functor, we would need a leaf to the category of topological spaces. I mean this. We need a leaf. The proper name is rigidification. Okay. Okay. This is the category of topological spaces. Now, this is B, the functor B. This is a rigidification of B. Okay. Now, now we can take the homotopical limit of this functor.
May I briefly ask in what sense this classifying space you've written down as a classifying space, what it classifies?
The name?
Like
BDI,
classifying
BDI4?
spaces- Yeah, usual classifying spaces classify bundles, but for a fusion system, presumably they're classifying something a little more exotic.
Okay. Well, it's the name is not now because of it classifies something, but for instance, when we have this guy, the p-completed BG, we say that this is the classifying space of the fusion system of G over S.
Okay, so you want a general construction that in those special that generalizes this case, that in
Yes.
these special cases spits out.
Yes, that's why.
Why do you require this B tilde to be strict rather than just say you want some homotopy coherent lift to a higher category of spaces?
Why we need a rigidification?
Well, like generally you could compute the homotopy colimit if you had any lift to the infinity category of spaces such that that diagram commutes up to equivalence.
Oh, well, yes, probably, but I don't know all the details, but this functor, as it is defined, it's problematic to construct the homotopical limit. So we needed a lift
Right.
to.
No, like you need a lift, but why to top rather than to the infinity category? Why force it to be strict?
Well, maybe because yeah, maybe it could be generalized, probably. Yes.
Yeah.
You just have to specify the coherence.
Yeah, probably could be more general. Yes, you're right.
Yeah, so the infinity category is all limits and co-limits, and those agree with the homotopy limits computed in the model structure. Yes, I mean, in some sense, it's a related problem, but sometimes you get like the homotopy coherence, you need to thicken the source category, or sorry, sometimes you get rid of the homotopy coherence, you need to thicken the source category.
Lifting is a detail.
Yeah.
An existence and uniqueness of linking system.
Oh,
This
yes.
is Chermak's version.
Yes, the lift is unique, essentially unique. Yes.
Yeah, so it seems to me like maybe the existence of liftings is easier in the infinity categorical case, although writing them down explicitly is obviously going to be a trick.
Would be interesting.
Well, if you are curious about this space, let me include this. The space BDI4, this the classifying space of these two compact groups, is important because if its cohomology realizes the mod 2 Dixon invariant of rank 4. Before this construction, people still believe that there might be a company group whose classifying space could realize this cohomology ring, but there is no such a company group, but something close to a company group, a two compact group, exotic two compact group. So well, it was one of the motivation of Dwyer and Wilkerson to define this space. Okay. If you want to realize the mod 2 Dixon invariant on rank 5, it's impossible because there is no space that realizes that cohomology ring. Well, okay. Well, going back to the lifting, the homotopy limit of this lifting will be homotopy equivalent to the classifying space of the fusion system F. Okay. Chermak proved that there exists, proved the existence and the uniqueness of this classifying space of F. This,
So when you write BF, you're not talking about the classifying space of the category F, it's something else.
well, an actual definition is this one. Oh, sorry, I have to be complete acá, here. The classifying space of F is the geometric realization of a certain category related to F induced by F. This is a space. Yes. You have a category.
So the theorem is the existence of L.
Essentially, yes. Essentially.
BF is just a notation. It's not the classifying space.
Yeah.
It's not the realization.
So, what? Now, I don't know if I should call this proposition or theorem, maybe theorem by Chermak. Well, let me know if I'm wrong, but Chermak proved that any fusion system, saturated fusion system, can be realized by not necessarily a group, but by a locality. Maybe we might confuse with this. This is a central linking system, and this is a locality. Maybe another notation. L. Okay, where L is a locality. So any fusion system can be realized by a locality, and a locality is a particular partial group. It's a partial group with a very well-behaved p-local structure. A particular class of partial groups. Okay. Now, but what is a partial group?
Partial group language. Do you also have uniqueness, or is it just true for linking system? Do you this locality is it unique for fusion?
Well, yes. From, if I remember well, from a locality you can induce a centric linking system. From the centric linking system, you can recover a locality. Yes, they are equivalent notions. Okay, but L if is a partial group. Now we will define this notion. Partial groups. A partial group is a tuple and the pi and the inverses where D is a subset of the words of M. What are the conditions of D? Well, M is contained in D. The elements of M can be seen as the words of length 1, right? Okay. Another action of over D is if the concatenation of these two words, U and B, belongs to D, then both U and B belongs to D. Okay. Now, pi, the product, is a function from D to M. So it takes certain words of M, and multiplies them, and gives you an element of M. Where with some properties. Pi restricted to M is the identity. Well, this is the most natural action. The following action is maybe not super intuitive, but anyway, I would like to mention. This circle means a concatenation of words. Okay? So if the concatenation belongs to D, then this other concatenation belongs to D. Now, another action for pi is this one. Okay, maybe I am missing one action, but actually, the actual definition of partial group is quite technical. So I only wanted to remark these more interesting properties or well actions. Well, the identity is the image of the empty word. So this is the definition. This is the word empty. The empty word. And we have the inverse function. Bijection. It's involuntary bijection, such that if U belongs to D, so the inverse of U belongs to D, and as you imagine, this is one. Yes. Okay. Let me check if I forget something. Okay. Yes. Sorry.
I think the elements of M are letters.
I don't know. Yes.
D is a set of words. M, I think of letters, aren't they?
I think you apply the inverse.
Pro.
and applies to the word.
Yes. Okay. Maybe it's a typo in my notes. Sorry, but
We have seen like a definition of this.
let me check my.
The same or there's something?
Just a moment. Hello. Thanks. Yes, if we have a word, let's say this.
Would it be possible for you to dictate what you write?
Sorry?
Would it be possible for you to say what you're writing? Because I can't actually see it. If you speak what you're writing, then I can understand what the formula is.
Oh.
Or is it because of the pen, or is it?
Well, it may be the pen or it may be mathematics,
Because the top part is dying
but
out.
for example, the top accent, I have no idea.
You compose with D, compose with W. If you apply pi, that's the same as pi of V composed with pi of V composed with W.
Right. So I was just asking you to read that.
Okay. Yes. Yes, indeed. This bijection can be extended to all the words in D by this convention, right? This is how.
Probably reverse order.
Yes. Yeah. We inverse all the.
You reverse the order, right? So it's Fn to F1.
Oh, sorry. Yes. Yeah. Yes. I reverse the order. Yes. Well, yes. Well, maybe an example is a good idea at this point. Okay. GCOM. Well, GCOM as a set is G. Well, let's suppose we have a group G. GCOM is a partial group that as a set is G, but this word belongs to D. Well, if this has a length n, we said that this belongs to Dn, the words of D of length n. If and only if
We look at an element of M as a word of length 1, correct?
yes, n, yes, that's why, that's true. Okay, if and only if they commute pairwise. Okay. In that case, in the case the components commute pairwise, the product of this word is the usual product. G1 for G2 for Gn. Okay, so as you see, not all a string of elements can be multiplied in this in GCOM. Well, I'm sorry, I don't have a explicit example of this, but we might imagine that this is true.
Could you change the one marker from the
It's very thin, right?
this is new?
Yeah, just the brand new one.
Okay.
Maybe not used enough. Maybe I
Okay, maybe it'll be okay
should,
after.
maybe you should thicken a bit.
Okay, I will try. I will try. Okay.
Yeah, but this is brand new.
This situation might occur. Let's suppose that G1, G2 belongs to D. So these are admissible word. Okay. It might occur. Sorry, G1 multiplied with G times G2. And this is not an admissible word on length 3. You can see why. Well, let's suppose we are in this case. Yes, we are using the partial group GCOM. G1 and G2, this pair belongs to D, so they commute, okay? And this other pair belongs to D, so G3 commutes with G1 times G2. But this is different. But here we need another condition. We need that G1 commutes with G2, G2 commutes with G3, and G3 commutes with G1, which is not is not fulfilled by this previous condition. Okay, so that's why, in this sense, it's different to the classical notion of a group. Okay? So the associativity condition is not present here because yes, we often believe that by the associativity property, we could believe that this tuple is an admissible word, but it's not the case in general. I will try to get an explicit example of this, maybe for another talk. So we can speak of partial subgroups, homomorphism of partial groups, etc. Okay, now another point of view for partial groups is given by Broto and Gonzalez, because to any partial group we can associate a simplicity set, but this simplicity set, from this simplicity set, we can recover the original partial group. So well, let me check my notation. Okay, suppose we have the partial group M. We can induce the nerve of M. This is a simplicity set. And this is a partial group. Okay. The end simplices of this nerve are the admissible words of length n. And well, probably you imagine the phase maps, but I will.
Why are all these nerves not DM?
Well, at least I prefer to call to use the notation PM for the realization of this implicit set.
Oh,
Yes. So we can talk about we can speak of the classifying space of the partial group M. Yes. Yes. Surely everybody here imagine which are the phase maps, but maybe for somebody in the virtual room, I will recall the definition. Okay, let's suppose we have this admissible word of length n. We have this shorter word if I is 0, product of m I, comma m I plus 1, which later will be denoted simply. Do I have other colors? Okay. And n. If I fits in this interval, and at last when I is n.
They can be equal to -1.
Yes, sorry. Okay. Well, the degeneracy map is more natural. We only include an identity. Okay.
The definition of partial group, I guess subletters of letters in D are also in D, right?
Sorry? Yeah.
The definition in the data for partial group.
Okay.
So D is the admissible letters, right?
Admissible words,
Yeah,
yes.
admissible words. So subwords of admissible words are also that condition. It was written? Okay, sorry. Yeah, okay. And that's why
Yes. Yes. Yes, and this big word is admissible, so these subwords are admissible.
it also for the degenerate.
Yes, yes, yes.
I think not obvious to me. But why is it admissible if you add one?
This guy?
No, this one. One stroke, yeah. I think one is why is it
Why this is admissible?
There's the axiom that's like
Uh,
U of pi of v of w, but you can write any word by sticking an empty word in. And so just applying pi to the empty word gives you that one.
yes. In particular, the empty word is admissible always. Yes. Admissible. The empty word is always admissible. Yes. Well, a little observation. The nerve of GCOM, the n simplices, can be identified with the homomorphisms from Cn to G. No problem with that? It's not hard to see. now the realization of the geometric realization of this implicit set is denoted become of G, and it's called it's known as the classifying space of G for commutativity. Right? That's the name, right? The standard name.
Yeah, classifying space.
For commutativity. Good. Okay. Maybe another example. Quite similar to this one. We might denote it GCX by contextuality. As a set is the set of elements of G of D torsion. This maybe this is not a standard notation, but I will clarify this here. G D equals 1. D is a well, in principle is you can take it as any integer, okay? But maybe the interesting are when D is a prime. Now again, very similar. The words here are admissible if and only if the components are pairwise the commuting. Okay, again, G1. Okay, and now this detail is important because, for instance, G1 times G2 to the power D is G1 power D, G2 power D, because they commute. In general, it's not true. So this is 1 times 1, it's 1. Okay, maybe, well, this example is of particular interest for contextuality, quantum contextuality.
How long are you planning to go?
Oh, well, if time is short, I expected to have more time or maybe give another talk for other chance. We are 1 hour, right?
So we go between 1 hour and 1 hour, like 90 minutes. So
Oh,
how long do you want?
maybe 15 minutes more.
Okay.
Possible? Okay. Gabriel-Zisman cohomology. Okay, well, everybody here knows what a simplicity set is. Given a simplicity set x, a coefficient system of x in R mod is a functor functor A from the simplicial category to the category of R models, where well, the objects of with this object and dysmorphisms where is a non-decreasing map and in use of f valued if g is x. Okay. So we define the cohomology of this implicit set X with coefficients in A, in this coefficient system, as the cohomology of the following complex cochain complex. Where is the product of these guys. Okay, this is an abuse of notation. I should write here x n, but it's redundant, so I only write a of x. Um, minus 1i Okay, I use this notation. Okay. Well, now with the Gabriel-Zisman cohomology, this generalizes the cohomology of categories. So no problem with that aspect. Example. C is the category of G. So I would like to finish with this, and well, I would like to complement with further talk maybe in the future. I don't know, but this part is important. Given a RG model M, it is induced a photo and underline bar. Of course, this is a group, but it can be seen also as a category. Okay, G is a category with a single object, and okay, yes, this is the automorphism given by G. This is an automorphism. Okay, so the cochain complex. This case, A of X is M, and the index, this product runs over this tuple, and this is the same as the function from Gn to M. That we are familiar with this cochain complex. We can also use this formula and we will obtain the usual formula for the cochain complex of in-group cohomology. Okay, so yes, the time was short. I would like to book another session to complement this talk. Yes.
Okay, thank you. Any questions for Victor?
So this basically appears to be like a generalization for some pre-sheaf modules of the unnormalized chain complex function of a simplicial set. Is there an equivalent, like more chains version of it?
Another, yeah, I was trying on that question, but it's not direct. At least it's not trivial. Yes.
Okay.
Yeah.
like more chains, normalized chain conflicts. So the actual functor in the dual complex.
I mean, the differentials aren't using the S maps, right? It looks to me that those can be modeled out in the way we do for normalizing G complex, but I don't know, maybe the A
Right.
creates difficulties.
This is why I asked, because it looks very much like exactly the same setup. So you would think you could mod out and get a nice normalized chains functor, but I don't know if twisting by this coefficient.
Well, this is Gabriel-Zisman cohomology was necessary to define the partial group cohomology because, as you remember, a partial group can be seen as a simplicity set. So, in this case, we will replace the simplicity set by the nerf of the partial group, so we can define the cohomology of my partial group. But we would like to define the partial group cohomology, the cohomology of a partial group with coefficients in another partial group. This is maybe no trivial.
Wait, what, could you repeat your last sentence? You want to define cohomology for partial group with coefficient
In another partial group.
in another partial group. Okay, so could I take a while this?
Sorry?
Could I take a while this? Those would be something like partial group.
The thing is that there is a notion of extension of partial groups. So we can speak of the class of equivalences of extension of partial groups.
Yeah, that was
So-
gonna be my question. So is it not, for instance, that H2, I guess, classifies those?
H2,
So which cohomology classifies extension?
H2.
Yeah, so
uh,
the H2 here for partial group.
yes, the second cohomology group for partial groups also classifies the extensions, the isomorphism class of extensions.
Yeah, so in my opinion, it would be interesting to extend, you know the description of H3, for instance? The two categorical understanding.
Uh,
So basically giving a cohomology class, like defining an associated for two categories.
well,
There is this, there is this thing.
I'm not quite familiar with two categories. So
Yeah, so there is this interesting thing, and it was known since since McLean in the 50s, I guess. People knew this. In the partial case, could be interesting. Some sort of partial by category. Where, are you following, Walker?
yes,
Are you following?
Sorry, I'm thinking about unit extensions.
Oh,
Sorry.
So do you think it's difficult to do partial
yes,
or by
of course.
categories?
My first attempt was trying to see a partial group as a category, but the associativity property was not present because you have a category, you have an associativity property.
Yeah,
Yes, but partial groups lacks of that property.
yeah. No, I'm just, it would be interesting, I think, to look for. You might end up with an interesting object. That's what I'm saying. Of course,
Oh, okay. Well,
we can talk about it.
yes. Time was short, but I think it was proper to introduce the origin of this definition. because they were originated in the context of ocean system and compact groups and.
So Chermak's definition of locality is a particular kind of partial group, right?
Is a particular partial group, but with a well-behaved p-local structure. Yes. In general, we don't have that. In general, yes. Because maybe Cihan, you remember the classifying space of C2. I don't remember. Let me check my notes. I believe is sigma 3 com. My notation is sigma 3 com. If I remember well, it was a bouquet of as a wedge sum of other classifying spaces. Yes. So too locally they don't behave well.
Complete or something? That would be a Z-3 there.
Maybe I don't remember well, but well, I will have the example for the next talk. Yes, but I remember something like that. There is the composition of the homotopy type of the classifying space of a group for commutativity. Yes. Is it right?
No, you have to choose complete on the left hand side.
Oh, okay. Okay.
But even then it wouldn't be true, I suppose, because of the wedges. But yeah, you need a Z mod 3 on the right hand side.
Mod 3. Okay. Okay, so would be okay. Mod 3. Yes, but in general, partial groups don't behave well p-locally, unlike the localities that are well behaved. Yes.
Like your question, I don't think Gabriel-Zisman Degeneration question. Like, unless it is local coefficient system, which is defined on the fundamental, to have the property that okay.
Oh.
Doesn't behave like you can even
Right.
you can get very crazy.
Right. Basically because the degeneracy maps on the level of algebra are not going to exhaust all of the things.
Construct an example.
Yeah.
Okay, any other questions? If not, let's thank Victor again.